All right, so let's give a formal definition of homomorphism. And we saw before that homomorphism is similar to isomorphism, so we should expect the definitions to be similar. All right, so here's the definition right here. Homomorphism between groups G and H is a function f from G to H such that f of G1 times G2 equals f of G1 times f of G2. This is simply the statement that it preserves operation. Well, it's not working very well. It preserves operation, okay? So this dot is the operation in G, and this circle is the operation in H. The range of f and H is called the homomorphic image of f. So let me just draw a little picture over here. Here's G, and here's H. Those are my two groups, and here's my F. Okay, now the homomorphic image is not necessarily all of H, so the homomorphic image would be somewhere here. And what we're saying is that if I have G1, G2, and then here I would have G1 dot G2 somewhere here, and then here I would have f of G1 would be somewhere over here. F of G2 would be somewhere over here. And then f of G1 circle f of G2 would be somewhere over here. Okay, but this G1 maps to this G1, this G2 maps to this f of G2, and this G1 dot G2 maps to f of G1 circle f of G2. All right, so that's tying all those things together. All right, some examples. Now, we can do homomorphisms with finite groups or with infinite groups. Okay. Now, if we have an infinite group, we can't do a Cayley table. Well, let's look at this example. So here's the circle group consisting of all complex numbers such that the absolute value is equal to 1. So you can visualize that. I think there may be a picture down here. Let's see if we can have it. Yeah, okay. So that's the circle in the complex plane. Now, imagine the real line wrapping around this like it was a tape measure. So let's go over here and see if we can do some more. Yeah. So we're going to have the real line here, and we have the circle. And the idea is that we're going to wrap the real line around this circle. All right, so here's our real line. Let's go. I'm going to mark this off 0, 2 pi, 4 pi. You'll see why in a minute. And then here's minus 2 pi, etc. All right. So if we wrap this out, and for every 2 pi units, the real number started on the circle again. So we're identifying the real line with the angle along the circle. Right. So this would be 0. Here we go out to pi over 4. Right. So we're going to take this point here. So if that's pi over 4, that will go to this point here. If I have, well, this looks like pi. Pi would go over to here. So we're wrapping elements of the real line around the circle. Now, of course, 0 and 2 pi will go to the same place on the circle because it's the same angle. 0, 2 pi, 4 pi, etc. So this mapping is not one-to-one. But it is a mapping between groups. We have the additive group of real numbers, so this is R plus. And then this is T with complex multiplication. So we can say that if we're going to take some mapping, we can say a mapping X goes to cis of X. That's our mapping. And that will take real number to a number on the circle. So here we have Z equals cis alpha. That's what he's talking about here. Right now, suppose we have cis alpha plus beta. And you can do this angle addition formula and show that cis at alpha plus beta equals cis at alpha times cis at beta. So look here, this plus here is the operation in R plus. This times here is the operation in T, right? So we are getting an operation preserving property. And we have a function that's not a bijection. So in fact, we have a function between groups that's not a bijection that preserves operation. This is a homomorphism. And you can see some of these properties of this. Right? So, for instance, cis of all of these angles, 0, 2 pi, 4 pi, minus 2 pi, minus 4 pi, they all go to 1 on the complex circle. I put a 0 here, that's just because the angle is 0, but the complex number here is the complex number 1. Right? And then we'll talk about cosets of this group. This is a group, this is actually a subgroup of R and has cosets. And there's going to be a relation between the cosets of this group and the points on the circle. Don't know why it disappeared like that. Let me get it back. So that's something that you can explore. And it's similar to the explorations that we made in the first section of this chapter. All right. Now, there's another homomorphism also between complex and real numbers. Okay. Now, T is inside the complex numbers. It's not all the complex numbers. But we can use T to create a different homomorphism. Let's see how this works. Every complex number in T has modulus 1. They all lie in the circle of radius 1. If we increase the radius of the circle to 2, all the complex numbers have the same modulus 2. And you can keep increasing or decreasing the radius of the circle. You can catch all the numbers in the plane with the concentric circles that you've created. So bottom line is that we can map every complex number, this is an arbitrary complex number, to the radius of the circle that it lies on. So for example, let's see if this works. Let's draw some circles. Complex plane. I'll draw some concentric circles. Suppose, for instance, this here is R equals 1/2. Right. And according to this function, every point on this circle will map. It's not actually mapping to the whole real line, it's mapping to positives. And I'm going to leave off the 0. Every point on this circle is going to map to the real point 1/2. Every point on this circle, R equals 1, is going to map to the point 1. Every point on this circle, R equals 2, is going to map to the point 2. So I could show this with colors a little bit better if I wanted to make this, let's make this red. Everything on this circle here is going to map to this point. Everything on, let's be green, everything on this circle here is going to map to this point. Under this mapping, f of r cis theta equals r. Right. Now, here we're also excluding the point 0 from the complex numbers because we want this to be a multiplicative group. So we're excluding the 0 point here. Excluding that. And as I said, we're excluding the 0 point here. So we have positive real numbers, R plus, related to C star. C star has multiplication, R plus has addition on it. Okay? No, I'm sorry, R plus also has multiplication. Sorry about that. Right. If you multiply, because we don't have the 0, but we do have the 1 in there. Okay, so we have the mapping, and we have our two groups. You can show we have the, this shows that we have the operation preserving property for the homomorphism. So in fact, we have a homomorphism. And here's some other exercises that ask some other questions for you to explore about properties of homomorphisms. Okay, some more exercises. This one involves determinant. Determinant is a mapping from the matrices to the real numbers. And you can see how that works out. So let's see, go down here. Okay, and here's one more example of groups where we're doing a general group and not talking about specifically. We're taking group G and a particular element in big G, and we're forming the powers of that element. And we know that the powers form a cyclic subgroup. Remember this angle brackets G. Do you remember? Just remember how you do that. Angle brackets G is equal to, let's change from pink. That's go to here. You know that angle brackets G, in general, whether you have finite or infinite group, you're going to have G, G squared, G cubed, etc. You're going to have ID, and you'll have G inverse, and so on. So we know that this is actually a cyclic group. And we can do a mapping from the integers into this arbitrary group by f of n equals g to the n. So we can do this actually for any group element of any group. So we get a homomorphism from the integers into any group G. It's going to be the homomorphism from Z onto this cyclic group generated by G. And we'll get some properties for that too. Right. This exercise talks about how inverse relates to homomorphism. For instance, if I have a group element G, it's not taking me, it's not going there. If I have a group element little g, okay, whoops, there we go. Finally took. Okay. So, and if F is a homomorphism from G to H, and I take F of D, and I take F of D inverse. So what's the relationship between F of D inverse and F of G inverse? Are these two related? Well, that's what you'll investigate in this exercise. Okay, so it pretty much covers the content of this section, and we'll stop there.